Thank you.
So I'll talk about this paper on self-organized localization based on work with Jan Giudice and Matthew McCullough here at CERN. And you can find more details in this paper, where all the technical details are in a lengthy appendix. So the main story that I want to tell will start with some motivation based on naturalness problems in effective field theories, and how looking at the phenomena of criticality and quantum phase transitions in cosmology could address some of these problems. Concretely, this is using the framework of the Fokker-Planck equation, in particular with the volume expansion dynamics in inflation. And I will give some description of how these dynamics are described by this equation before adding to this description the key ingredient of quantum phase transitions. And this is what leads to the phenomena that we call self-organized localization. Once I've described the framework that describes this quantitatively, I will apply this to some potential solutions to naturalness problems in our universe before concluding with a brief discussion of the measure problem in eternal inflation. So please feel free to stop me at any point if you have any questions. The motivation behind trying to understand better what may lie beyond the principles of effective field theory is that our effective field theories have been incredibly successful and yet still have certain problems that seem to require something beyond these principles. So as Weinberg and Wilson taught us, the reason that our current fundamental theories, such as the standard model and general relativity, are so successful is not because they are fundamental renormalizable quantum field theories in the sense that people used to think of in the 60s, but is because they are effective field theories where all the higher dimensional operators also have to be included to the standard model Lagrangian. So this means in particular dimension 5, dimension 6, 7, 8 operators and so on. And the reason their effects have not been seen is because they are suppressed by some heavy scale of new physics. In the case of the dimension 5 operator, this is the famous Weinberg operator that describes neutrino masses. So in some sense, we may even be seeing the leading order term in this effective field theory expansion. So this framework has been very powerful in terms of understanding the features that perplex the previous generations of physicists, such as the accidental symmetries, which are well understood from an effective field theory point of view. And moreover, they give natural expectations for the sizes of parameters based on power counting and symmetry arguments that tell you as a naive order 1 expectation what you should get for the sizes of the dimensionful and dimensionless parameters in this organizing principle. So this sound reasoning has been vindicated many times in the past, such as predicting the appearance of the Rho meson, such as the appearance even of quantum mechanics based on classical electromagnetism for the self-engined electrons. And all these naturalness arguments have been well explained in the past. So this leads to the famous hierarchy problem of the Higgs mass, this dimension 2 operator, for a scalar is not protected by any symmetry. So one expects this value to be at the cutoff of your theory, of the effective field theory of the standard model, which if that cutoff scale is very high, the fact that we measure the Higgs mass to be at the electroweak scale is a puzzle that seems to require a fine-tuning by hand to get the desired value. And the cosmological constant is an even more severe problem where this parameter wants to be at the cutoff of the theory, but the measured value is at the 10 to the minus 3 electron volt scale rather than the cutoff of the theory. So this seems to require an even larger fine-tuning. So this suggests that effective field theory, despite being very successful in understanding our theories, is not the whole story. So what could be a potential principle that may help explain some of these puzzles. Critical points are one type of phenomena that is very interesting, because all of these problems that I mentioned of naturalness can be seen as a fine-tuning to live at a critical point of our theory. So to be at the critical point of a classical phase transitions, we know requires tuning, such as the phase transition between liquid water and ice is something that requires dialing the temperature to be right at the transition point. So a fish living in a pond where the water is just at the edge of freezing over, but hasn't quite frozen over, might be a puzzling situation for the fish. The fish would be wondering, why am I not living in any of the purely liquid phases, and I just happen to be living at the boundary of a critical point where the water is about to freeze over. So it's a highly non-generic point to be living at. And there are three hints that we may be in a similar situation as the fish, but in our universe itself. So the first is the measurement of the top mass, and the Higgs mass tells us in the standard model with no new physics that the vacuum, which could in principle have been anywhere in this island of stability, or even in the unstable region, which would mean that without new physics, our vacuum would have decayed to a deeper vacuum a long time ago. Instead, we happen to just be on the edge of stability and instability, where our vacuum is just about long-lived enough that we survived until now, but not quite in the complete stability region where there isn't a negligible probability of decaying. So it seems that the standard model Higgs potential is living dangerously on the critical boundary of these two phases coexisting. The Higgs mass naturalness problem that I mentioned before can be seen as us living very close to the boundary, the critical point between the ordered and disordered phase of electroweak symmetry breaking. So the Higgs mass quadratic term could have been anywhere from minus the cutoff of the theory squared to plus the cutoff of the theory squared. And instead, we are living at minus 246 GeV squared. So this is also seen in the cosmological constant, as I mentioned before, where we seem to be living at a value of the CC that is very close to the boundary between an imploding and an exploding universe, depending on if we have a negative or a positive CC. It happens to be a very small positive value. So all these three hints suggest that we live at a very special point close to criticality in our universe, just like the fish living in a pond where the water is just about to freeze over, but hasn't quite yet. So this could be answered in many different ways. For the metastability problem, well, this isn't a problem in itself, and the Higgs potential could trivially be restored by having heavy new physics that couples to the Higgs that changes the RGE running of the Higgs quartic and restores stability. For the Higgs mass, this can be solved in the usual way of having new symmetry-based physics beyond the standard model, such as supersymmetry or composite Higgs models that restore the naturalness of the Higgs mass by protecting the quadratic corrections through the addition of new symmetries. And this is an argument that that uses the effective field theory organizing principles of symmetries to understand the sizes of parameters. On the other hand, we know that these arguments don't work for the cosmological constant. Supersymmetry or other symmetry-based solutions don't seem to work to explain this particular problem because the scale is so low, and we would have seen this new physics already if it was there. So the only viable explanation so far has been in terms of anthropics. Alternatively, what I want to discuss today is that these may hint at a new principle beyond the usual symmetry-based effective field theory principles. So this is the phenomena of self-organized criticality, which is something that we know exists in nature. We know that many systems self-tune themselves to live near criticality. So a famous example, and this whole field was initiated by Tang and Wiesenfeld in 1989, where they give a simple example of a sand pile. So the sand pile is a self-organizing system in the sense that when the sand grains accumulate, given enough time, the slope of the sand pile will always be the critical gradient, such that the sizes of avalanches triggered by each grain of sand falling on the slope follows a pink noise distribution. That means that if the slope was shallower, then every time a grain of sand lands, it would never trigger a big avalanche. If the slope was steeper, every time a grain of sand lands, it would trigger a huge avalanche. At the critical gradient, the probability of triggering the avalanche follows a distribution that is scale invariant and is known as a pink noise distribution. So an ant living on the sand pile might find itself wondering, given all the possible gradients, why do I happen to live at the critical value of the slope? And the answer is just that given sufficient time, through the interplay between the microscopic dynamics of the grains of sand and the macroscopic dynamics of gravity acting on this pile, given enough time, the slope will always end up self-tuning itself to be at the critical gradient. And since then, there have been many other systems in nature that have been shown to self-organize itself to live at some critical value. I give in the middle here an example of a recent theory that has gained acceptance, which is the neural connections in the brain, where neurons trigger an avalanche of signals in other neurons, also happens to self-organize to live at a critical point where the sizes of the neuron signals being triggered are not quite too ordered and not quite too chaotic, but happen to be at this boundary. So the brain, in some sense, is also a self-organized critical system. And since then, we've had many examples in nonlinear dynamics, systems theory, finance, networks, evolution, and so on and so on. Okay, so how do we actually use this idea of self-organized criticality to explain how the values of our fundamental parameters in our quantum field theories could somehow self-organize to be at critical values? We need a mechanism, and this mechanism is using cosmology in some way. And this idea has this similar sort of approach has been pursued in the past in these nice papers by Justin Corey, using a very different setup to ours, but the same idea of self-organized criticality. In this case, it's an eternal inflation landscape of vacua, and the dynamics are very different to ours, where we look at a single vacuum and we look at a effective field theory patch along that vacuum, where we look at a single fluctuating scalar field. So it's a very different approach. And in our case, we find that the quantum phase transitions during cosmology are what localizes the fluctuating scalar fields at these critical points. Okay, so the last part of the introduction is just to explain what I mean by a quantum phase transition. This is just as opposed to a classical phase transition, where a background temperature can be varied to go through a phase transition. In a quantum phase transition, by that I just mean we vary a background field to trigger the phase transition. So if we take this example potential, then the psi scalar field potential, when the value of phi is 0, has this Z2 symmetric form with the two vacua, and psi could be sitting at one of them. And when phi varies its value, we can see that this coupling breaks the Z2 symmetry and introduces a tilt in the potential. And when phi becomes large enough, then at some point, the psi scalar field will transition from one vacuum to another, which is what I mean by a phase transition that is quantum, as in it is not triggered by thermal fluctuations, but by some background field. Okay, so these are all words to describe the bigger picture of what's going on. Concretely, to quantitatively describe this, we use the Fokker-Planck equation, which is the semi-classical approximation that Starobinsky pioneered to describe the fluctuations of the zero mode of scalar fields. When they undergo classical slow roll during inflation, they also get stochastic kicks from Hubble fluctuations. So the Langevin equation describes at each time step the evolution of the scalar field with classical dynamics, and this eta term is stochastically drawn from a Gaussian distribution of Hubble width. So you can imagine this is like a random walk with some potential gradient. And if you take this trajectory for the scalar field and average it over many, many trajectories, then you get a probability distribution over this ensemble of trajectories. And you can show that the ensemble averaged Langevin trajectories can be described by the Fokker-Planck equation. So this Fokker-Planck equation is, if we ignore the volume term, then the Fokker-Planck equation is a normalized probability distribution, where the first term in this equation describes the quantum kicks that it gets. So this is known as the quantum diffusion term. The second term describes the classical drift. And without this term, P would be a normalized probability distribution. What also happens during inflation is that when a scalar field explores different parts of the potential, then the exponential expansion during inflation prefers inflating volumes higher up the potential with higher energy density, exponentially more than lower down the potential. So this introduces this volume term, which means that the P here is no longer a normalized probability distribution, it's now a volume distribution. And the size of this volume undergoes fluctuations plus an expansion higher up the potential. So the size of the volume is what tells us the probability of phi taking on certain values along the potential. The larger the volume, the more probable it is for an observer to find itself with that value of phi. So during inflation, there is some ambiguity in how one chooses the hyperssurface slicing of constant time. This is known as the measure problem in eternal inflation, because in eternal inflation, essentially there is an infinity in the volumes that require some regulation by choosing a particular slicing in some way. So this is parameterized here by this what we call a time gauge parameter, psi. And this psi, when it's equal to 1, is the usual proper time value, the proper time parameterization. And when psi equals 0 is known as the scale factor parameterization. So we'll work in proper time for now, but I'll come back to this dependence on psi. So it's important to remember here that the phi field that we're describing is not the inflaton. We call this an aperon field, and this phi field is essentially fluctuating in a background of inflation. So inflation is happening in some inflaton sector in the background that we don't specify. The energy density of phi is subdominant to the inflationary energy density. So we can expand around the constant inflationary value of Hubble, H0, where we treat the energy density of phi as subdominant. So a convenient normalization is to look only at the effective field theory patch of the potential, where we allow phi to fluctuate within the field range f. And this var phi here is an order 1 parameter, where we normalize to phi, the dimension full phi, to this field range f. We also normalize the potential by factoring out a dimension full f to the 4, such that this omega phi is a order 1 dimensionless parameterization of the potential phi. And this can be seen, we can always look at a particular patch of the potential along this effective field theory range and Taylor expand around there. And typically we only need to consider the linear term, the first term in this expansion. So we'll keep the discussion general by keeping omega phi, but you can imagine this is just replaced by a linear potential phi. So in this parameterization, the Fokker-Planck volume equation that I showed before takes this form, where alpha parameterizes the strength of the quantum diffusion. This is all in dimensionless parameterizations. Beta is a dimensionless parameterization of the size of the volume effect. So we see that this is proportional to the ratio of f over m Planck squared. And to have a sizable volume effect, we'll see that beta has to be greater than 1, which implies that the field range of phi is super Planckian. The time scale of the dynamics of this equation is normalized to this relaxation time TR, which is the time that it takes for a scalar field fluctuating with this value of Hubble to explore the entire field range F. So it's convenient to rewrite this relaxation time in terms of alpha beta times this value SDS, which is known as the entropy bound. And the entropy bound, SDS, is the ratio of m Planck to Hubble squared. And the reason why it's interesting to write it in this way, also this is labeling the different terms. I forgot to mention that the classical drift term in this case is just an order 1 number. So the reason why the relaxation time is convenient to parameterize in this way is that SDS is the maximum number of e-folds for non-eternal inflation. If the number of e-folds is larger than this SDS value, then we are necessarily in the eternal inflation regime. So this means that in the parameter space where alpha times beta is greater than 1, which we'll see is what we call the quantum regime, then the relaxation time is necessarily in the eternal inflation regime. Only if alpha times beta is less than 1 can the relaxation time be in the non-eternal inflationary regime. So without doing any explicit calculations yet, we can already see that if we have a sizable alpha times beta, we'll see that our mechanism has to be in the eternal inflation. We don't need to solve exactly the Fokker-Planck equation. We will solve this exactly for a linear potential, and we have results for a quadratic potential as well. And in particular, we don't have to solve for the dynamics, the evolving time dynamics, because what we're interested in is the asymptotic stationary distribution at late times. So if we write the volume distribution as a sum over eigenmodes, then we see that this we factor out the time dependence from the stationary eigenstate little p. Then we see that the eigenvalues are like the inflationary expansion factor. So at late times, when t goes to infinity, what is projected out of the superposition of all the stationary solutions is the distribution with the largest eigenvalue, since that's the one that will expand the most. So we are interested in the stationary distribution with the largest eigenvalue. And to determine this, we can then get the location of the peak, the maximum of the volume distribution. And this tells us what is the most likely value of phi. One way to obtain this without having to solve explicitly, though if we do solve explicitly, we get the same results, is to consider the physical criteria that the volume distribution has to be a positive quantity. It makes no sense for a volume to be negative. So given appropriate boundary conditions that you want your distribution to vanish, for example, on the edge of your EFT field range, this means that to satisfy the boundary condition, P has to just be going through 0 and just about to turn negative at the edge of your boundary. So the discriminant is a way of seeing how P is about to oscillate to negative values by looking locally at a point where we take this second order differential equation and we look locally by expanding at a point, it becomes a quadratic equation. And the discriminant of that quadratic equation tells us whether or not this is going to be negative. So the boundary condition requires us to have a 0 discriminant at the edge of the field range. And this tells us the maximum eigenvalue. And then the Fokker-Planck volume equation here tells us also the location of the peak, which is when P prime equals 0 by definition. So this gives us a relation between the eigenvalue and the location of the peak. So if alpha is small and beta is larger than 1, and this is an order 1 term, so this term dominates, this essentially tells us that the location of the peak is given by the eigenvalue. And we know the maximum eigenvalue from this argument. So putting the two together tells us that the location of the peak is at 1 in dimensionless field range units, which is essentially the edge of the boundary. So minus some order 1 number, omega prime 1 is the gradient of the potential at phi equals 1, so at the edge of the boundary. But this is just some order 1 number over alpha beta. So when alpha beta is greater than 1, this is negligible, and it tells you that your field wants to be as far to the right of your up the potential as possible. So let us look at an explicit solution, where here I take a linear potential, omega phi is just equal to phi. And this is the solution plotted on the right. So when alpha beta is much smaller than 1, as we saw in the previous slide, if alpha beta is smaller than 1, then omega phi now wants to be as far down as possible. This is the classical regime. If alpha beta is greater than 1, then, as I mentioned on the previous slide, the distribution, the peak, wants to be as close to 1 as possible, as far up the potential as allowed by the boundary condition. And there's also a Q squared B regime where it wants to be so close to the edge of the potential that it is bunched up at the end. And we can also estimate the width in a similar way by studying the FPV equation.
Excuse me?
Yep.
May I ask a question?
Sure, please go ahead.
What is the size of a typical size of a C in beta?
Of alpha and beta, you mean?
No, beta, C, psi.
Oh, psi, sorry. So psi, we set to 1 here.
Okay.
I'll come back to the psi essentially parameterizes the time gauge dependence. And in scale factor gauge, psi would be 0, for example. In proper time, psi equals 1. And different choices of hypersurface slicing could mean different values of psi. So for now, we work in proper time and just set psi equals 1.
Okay, I see. Thank you.
So this is essentially saying that what's important for whether or not the FPV distribution goes up or down the potential is not just the size of the Hubble fluctuations captured by alpha, and it's not just the size of the volume effect captured by beta, it's a combination alpha times beta, because you could have very small Hubble fluctuations. Alpha could be much smaller than 1, but a small Hubble fluctuation upwards multiplied by a very large volume effect will still mean that the inflationary expansion wants to carry the distribution up to potential. So this is captured by this plot of the parameter space alpha versus beta, where if beta is less than 1, then the volume dynamics are not so important, and we just have the Fokker-Planck dynamics of a fluctuating scalar field on a classical potential with getting Hubble kicks. But when beta is larger than 1, then the volume effects play a role in the dynamics. If the Hubble fluctuations are too small, then we can't take it to be too small, or the inflationary Hubble value will no longer be dominant, and the phi energy density will become dominant. So we require the phi energy density to always be subdominant to the inflationary one, and this is why we stick to the right of this plot. And the 3 different regimes that we're interested in that I mentioned before are the classical, the quantum times volume, and the quantum squared times volume. The quantum regime is just where quantum effects are so big that they just spread the distribution out with no interesting features. So we'll avoid also the quantum regime. Okay, so that's the dynamics of, yep.
I have a question on this classical and quantum regimes. So in the case of quantum regime, you show that the phi equal to 1 is favored. In the probability distribution is favored to peak around phi equal to 1 for quantum regime.
Yep.
Does it also depend? I mean, does it depend on the initial condition of phi? Or I mean, this classical, it seems that
No.
we have a classical rolling toward the negative value that I could understand, but the quantum regime.
So neither of them depend on the initial conditions, because essentially the initial condition is specified by this sum over the eigenmodes, and choosing the combinations of eigenmodes is what specifies the initial distribution. But as long as the largest eigenvalue is part of this sum, then the largest eigenvalue will always be picked out at late times. So the dependence on the initial condition is a statement about whether or not the initial condition contains that largest eigenvalue or not. So in some ways it is dependent. But if you take, for example, a Gaussian initial condition localized somewhere along this field range, then it will always end up picking out this quite generically.
So I think I can see from the equation, but you said that even for small quantum fluctuation, because of the large volume effect, the phi equal to 1 is favored in this Q square V region, right? So because the large volume effect, what does the large volume effect favor the region with a positive value instead of negative value?
Yeah.
I mean, because the contribution from phi to the potential energy is smaller than the inflaton energy, right? It's omega.
Yes, but it doesn't mean that it isn't taken into account. So the inflationary energy density is the dominant one that sets H0, but we still take into account the contribution from phi because that's what's described by the FPV equation, right?
I see.
So this equation, we are expanding around H0, but we're still keeping this contribution from phi.
I see. Okay. So
that's why it goes up.
I see. Okay. I understand. Okay. Thank you.
So now we can add the aspect of quantum phase transitions to this description. So take, for example, as a toy model, the linear potential that we described before, where we have the linear potential for phi. And then at some critical point, which we set to be at phi equals 0 without loss of generality, just by shifting coordinates, we can see that from this toy potential that I mentioned before, if phi is coupled to some other scalar field psi, and as phi is evolving along its linear potential, it's tilting the other scalar field psi that we're not showing here. So the psi potential is another direction. And after the critical point, psi transitions to its other vacuum. And the effect this has on the phi potential is to change the linear potential to a negative gradient rather than a positive gradient. So this is the potential that phi sees as it's exploring its field range. It triggers a phase transition and leads to a change, a discontinuous change in the gradient of its potential. So taking this into account in the FPV is that requiring continuity across the critical point gives a junction condition to satisfy in the FPV equation. This junction condition is no different to in undergraduate quantum mechanics when you solve the Schrödinger equation in a square potential, where you have to ensure the continuity of the wave function across discontinuous boundary conditions. You also have a junction condition to satisfy there. So if we solve the FEV equation again, but for the linear potential as before, but this time we also require continuity across the discontinuous first order phase transition, then we have this condition to satisfy, and the solution is then plotted on the right here, where we see again the classical solution, which wants to be as far down the potential as possible, as allowed by the boundary conditions, is now peaked at the bottom on both ends. And the QV and Q squared V solutions are peaked around the critical point. So this toy model is one way to see the effect of a phase transition. Another type of phase transition is this other system, where in this case we have what we call a hidden phase, phase H, which could have a very flat potential, and the visible phase it has a gradient. And again, as phi explores the hidden phase, it transitions off the edge and triggers a phase transition in some other sector, which leads to a change in the gradient. So it goes from one vacuum, it triggers a change in some other sector that leads to phi seeing a change in this sector. And again, there is now a condition to satisfy, which is the continuity of the flux. So there's a flux conservation condition for the volume distributions on the hidden and the visible phase when this flux transitions at phi t. So beyond the critical point, the transition need not happen immediately, as in the previous plot. It could take a while for this phase transition to happen, if it is supercooled in some way, that it wants to transition but hasn't quite yet. And then it keeps exploring until it reaches the transition point. So the flux conservation conditions are, again, ingredients that have to be satisfied when solving the FPV equation on these potentials. And the solution is again plotted on the right here for appropriate choices of boundary conditions. In this case, the boundary conditions chosen here are a non-vanishing flux on the edge of the visible phase, because in the classical regime, in the quantum regime, the solution will want to be as far up this linear potential as possible. Here we see that the solution is peaked for the visible phase at phi c, at the critical point. So it is peaked right here. The reason why it doesn't go all the way up is because this solution is in the C regime, the classical phase. In the C regime, the solution doesn't always have to go all the way down. Where it is located depends on the eigenvalue and the boundary conditions. So the reason it is peaked at phi c, unlike the linear potential solution before, is because we have these flux conservation conditions, which means the eigenvalue of the asymptotically stationary distribution on the visible phase has to match the one on the hidden phase. And this is what leads to the peak of the distribution determined by this eigenvalue being located at phi c. The probability to lie on the hidden phase is negligible compared to the one on the visible, as shown by this rescaling factor, so they appear on the same plot. So it is much more likely to be located on this visible phase. So this is rather surprising in the sense that from the point of view of someone living on this visible phase, there is no reason for the volume distribution to be located anywhere along this point. But because of the existence of this hidden phase, it wants to live at the point at which the vacuum energy is degenerate with the hidden phase vacuum energy. So we'll see why this particular solution is interesting now. So applying these solutions that we call self-organized localizations, because the volume distribution wants to self-organize itself to localize itself at the critical points. We can take the more realistic version of that pyramid potential that I showed before, where instead of considering a discontinuity at the phase transition point, as I mentioned before, that phase transition could take a while to happen. It could be a supercooled phase before the transition actually happens. So here we want to apply the setup to explain the metastability of the Higgs potential by having the quartic of the Higgs being scanned by our apeiron field phi. So again, we normalize, we shift the coordinates without loss of generality to have the critical point at phi equals 0. This means that when phi is negative, the quartic of the Higgs is positive. And when phi becomes positive, the quartic of the Higgs turns negative. And of course, when the quartic of the Higgs is negative, the potential of the Higgs drops. So diagrammatically, we call this the IR phase, where the Higgs is sitting at its IR vacuum, where the quartic of the Higgs is positive. And then in the UV phase, when the quartic goes negative, then we have this yellow potential, and the Higgs wants to transition from the IR vacuum to some UV vacuum. So we assume some new physics at the EFT cutoff of the theory will restore the Higgs potential. So as I mentioned before, the reason why in this setup we find ourselves living so close to the metastable point is precisely because the quartic of the Higgs is being scanned by phi according to this Fokker-Planck volume dynamics, where it's exploring the field potential, and the stationary distribution that it reaches is the one that wants to be close to the critical point. And this is why the value of the quartic is located in this metastable region. So we see plotted on the right, essentially the prediction on the m Higgs versus m top plane for different values of Hubble shown by the black contours. So 10 to the 8, 10 to the 10 GeV for Hubble tells us that we want to live somewhere along here. And the blue dashed lines is the value of the Higgs potential where the two vacua become degenerate. So this is maybe more intuitively seen in a plot of Hubble versus the cutoff of the EFT, big M. And the measured value of the Higgs and Topps mass tells us that the value of Hubble in this mechanism to explain the metastability has to be in the 10 to the 8 to the 10 to the 12 GeV range. If the cutoff is too large, then the inflationary energy density is no longer dominant. So we want to avoid this gray region here. And on the other hand, if the inflationary Hubble is too large, then the fluctuations are too large and the Higgs will no longer be sitting in its minimum. So we don't want to live in this gray region here. So this is the value of the parameter space that we have in this particular setup. So this is to understand the metastable value of the Higgs quartic. We can also apply this framework to understand the Higgs mass. So now we assume that the quartic is just the standard model quartic, and we have a different setup now where the scalar field phi is scanning the Higgs quadratic term. So now we have three different phases. We have the unbroken electroweak phase, where the expectation value of the Higgs is 0. We have the IR phase, where the expectation value of the Higgs as phi starts scanning to negative values is what we call the IR electroweak phase. And then just like before, we have the UV phase, where it has scanned so far that there is no longer even a IR minimum. So diagrammatically, this is in green, the electroweak phase, where the Higgs is sitting at its vanishing expectation value, because the phi value is still -1. So this is a positive quadratic term, and this is a positive quartic, which when you RGE to large enough values turns negative. As phi starts scanning from -1 to past 0, then it becomes positive and the quadratic term turns negative. And so we start getting the vacuum expectation value for the Higgs that we know. But again, as we RG to large values, we know that the quartic turns negative. And eventually, when phi becomes very large and positive, so the quadratic term becomes very negative, then we have this yellow potential here, where we don't even have a minimum anymore in the IR. We're left with only the UV vacuum. So this is the phase diagram in a sense, where we always have a UV vacuum at large values of the Higgs, because the RG of the quartic turns negative at large values. So the UV phase is always there, coexisting with the electroweak phase vacuum and the IR phase vacuum. But beyond a certain value of phi, the IR vacuum no longer even exists, and we're left with the UV vacuum. So the first question one might ask is, why didn't we use the unbroken to broken phase transition to self-organize to live at that point? The reason is that it's second order and a too small a transition to lead to localization, unless the cutoff scale is at the TeV scale, which is too low to be interesting for explaining Higgs mass naturalness. So instead, we used the phase transition going from the broken IR phase, which is sitting at this blue point, to the transition to the UV phase, sitting at this yellow point here. And again, solving the FPV equation requiring continuity of the flux conservation across this transition leads to the distribution localizing itself close to this critical point. So this makes a prediction for the value of the asymptotically stationary peak location that gives you the most likely value of phi is going to be close to the instability scale at which the vacuum drops over to the UV vacuum. So this says that the VEV V will be determined by the instability scale. And this instability scale can be much, much smaller than the cutoff M. So this gives a technically natural solution to the small value of the Higgs mass Unfortunately, in the standard model itself, we know that the instability scale at which the Higgs quartic turns negative is 10 to the 10 or 10 to the 12 GeV. So this is much too large. To explain a small electroweak vacuum of 246 GeV, we need to lower the instability scale. This can happen if the Higgs is coupled to some vector-like fermions, which induce a negative contribution to the Rg running of the quartic, and could lead to this turnover point being at the TeV scale. So we still have some little hierarchy to explain between the TeV instability scale and the weak scale. This is similar to the little hierarchy problem in composite Higgs mechanisms, where the Higgs wants to be at the composite scale F. So there's a little hierarchy between V and F. We have a little hierarchy between V and lambda I. This is not as ad hoc as it seems, in the sense that adding vector-like fermions at the TeV scale is motivated by naturalness, because any scalars other than the Higgs will want to be at the cutoff of the theory by naturalness, and any gauge bosons would also have to be at that cutoff if they get their masses from scalars. So unless there are other tuned scalars or vectors that are not gauge bosons, then we have some reasoning for new physics at the TeV scale being only vector-like fermions, and this necessarily leading to an instability that is lowered if it couples strongly enough to the Higgs. Okay, so finally, I want to end with the cosmological constant solution, which is the setup that I mentioned before of having a hidden phase that has a very flat potential, because this hidden phase could be a sector that is supersymmetric. So in our visible phase, supersymmetry is broken, but in the hidden phase, supersymmetry, and in particular R symmetry, protects the value of the CC. So if the CC is vanishing in the hidden phase, then through the mechanism that I mentioned before of the visible phase having a distribution that will want to localize at this critical point of the vacuum energy being degenerate with that of the hidden phase, is very interesting, because this vacuum energy is then going to be the one that gives you a vanishing CC. What is shown on the right here is explicitly the solution for the hidden phase, assuming vanishing boundary conditions, is given by this solution. This determines the maximum eigenvalue, which through the transition point is the eigenvalue that the visible phase will asymptotically have a stationary distribution, whose peak is determined by this eigenvalue. And this determines the peak to be at the vacuum energy that wants to match the vacuum energy of the hidden phase. And as I mentioned before, if we were in the quantum regime, then the solution on the visible phase would want to go as high up the potential as allowed by the boundary conditions. We are in the C regime, where the solution doesn't go all the way down, because if you solve the FPV, in general, you have two solutions, and which of these two solutions is picked out is determined by the boundary conditions. So what is crucial to pick out the solution that isn't the one that goes all the way down is to choose a non-vanishing boundary condition on the edge, which is some flux that is injected at the edge of the field range. And this is what picks out the solution that is peaked around the eigenvalue at the critical point. So after inflation ends, this constant inflationary value goes away, but this is an uplift of the vacuum energy that is the same for the hidden and visible phase. And so in our current universe, the location of the peak of phi will still be at the point of vacuum energy degeneracy with the hidden phase that has a vanishing CC. And as long as the slope is shallow enough that phi has not significantly evolved in the lifetime of the universe, then we would still see the value of the CC to be the value that is peaked around the vanishing CC. So let me conclude then with essentially the take-home message that scalar fields undergoing quantum fluctuations during inflation can be localized at the critical points of quantum phase transitions. And this is the non-trivial phenomena that we call self-organized localization. The key prediction of this mechanism is that our universe is somehow at the critical boundary of the coexistence of two phases. Whether that's the hidden phase of some supersymmetric vanishing CC, or whether that's whether that's the electroweak symmetry broken phase between some UV electroweak symmetry broken and IR electroweak symmetry broken vacuum, or whether that's the transition point between the quartic collapsing over. The measure problem is the big caveat to this whole framework, in that it is well known that during eternal inflation, because there will always be parts of the universe that is still inflating, the reheating surface at which these volume distributions tell you what is the most likely value that you would expect an observer to be in depends on the volume at the reheating surface. But we now have an infinite reheating surface, since there will always be some part of the universe that hasn't resurfaced yet. So how do you make sense of a probabilistic ensemble that is infinite? You have to regulate this by choosing a cutoff in time and asking at that time, what is the distribution? And then taking that time to infinity in some way. Unfortunately, this depends on how you choose the time slicing. And this is why this value of psi in different choices of the time slicing will give you different predictions. So there have been different approaches to solving the measure problem in eternal inflation. In our latest version 3, we discuss how this may not necessarily be a problem for making concrete predictions in some choices of measure. So the distributions that I showed before, despite having some dependence on the choice of psi, is related to the choice of how you want to solve the measure problem. And in our latest version, we give concrete examples of how this can be addressed in one choice of measure, such as a stationary measure, but it is not yet accepted what is the solution to the measure problem. So this is something that requires further study, in the sense that until we understand better the measure problem, the status of any kind of predictions, whether from SOL or any other FPV solution during eternal inflation, is still an open question. But the simplicity, in some sense, of this mechanism is highly suggestive of this type of mechanism potentially providing fundamental solutions to the problems that I mentioned before. So with that, I'm happy to end here and take any questions that you might have. Thanks.
Thank you very much for nice talk. Is there any question or comment?
I have one question. Thank you for a very nice talk. So I have a question on the scenario with the junction condition. So one with the visible and the other with the hidden sector. So so you showed two solutions. I mean, one in the visible sector and one in the hidden sector. I mean, you showed the two distribution. One is very sharp and the other is relatively shallow. But what does that mean by having two different solutions? So
you can see this as, I mean, it's one solution for the whole setup, but we have two different phases. and two distributions on that, but the solution is essentially the sum of these two.
Some of those two.
Yeah, so the probability is just much higher. The volume is much higher for the visible phase solution. This is why this 10 to the minus 213 is there. It's just to say that one could argue that yes, you have a peak here, but you also have a volume on the hidden phase, and it could well be that the observer is most likely to find itself living in this phase. But the explicit solution shows that actually the probability in the hidden phase is negligible relative to the visible phase. Yep.
It's very interesting. Actually, I'd like to understand this scenario a little better. So this is the solution for the global field distribution, right? Taking into account volume effect.
So there's, sorry, go ahead.
Yeah, if I just follow the scalar evolution in a given Hubble patch, so then how does it evolve? And classically, it will always go down on average.
So this is what is maybe counterintuitive about this solution is that, yes, if we ignore the hidden phase and we just take a linear potential in the classical regime, and you imagine a Langevin trajectory of a scalar field fluctuating along here, then in the classical regime, you'd think that, yes, the volume effect is not large enough for it to go up and it just goes down.
Right.
Now this crucially depends on so the FPV equation, on the other hand, if you actually solve this in the classical regime, gives you two solutions. It's a second order differential equation, and you have two general solutions. And these two general solutions, one of them is the one that will be all the way down, and the other one is going to be peaked somewhere along here, depending on the eigenvalue.
I see.
So there are two solutions even in the classical regime, and the only way to pick out the two is to specify more information, which is the boundary conditions.
Okay.
So if we specify a vanishing boundary condition, then this does pick out the solution that I showed before, which is the one peaked all the way at the bottom.
I see.
So crucially, if we pick instead a non-vanishing gradient at the boundary, so P prime at phi at the endpoint is non-zero, then we find the second solution is preferred. And that peak will then be somewhere along here, depending on the eigenvalue. So of course, we could just pick any eigenvalue we want, but crucially, this is where the hidden phase and this condition comes in, because this now tells you that the eigenvalue has to match the one on the hidden phase. And this is the eigenvalue that if you solve for the hidden phase, you have to match, and then tells you that that eigenvalue is the one corresponding to the peak localized here. So you can see this just by explicitly solving. It's a setup where once you specify the boundary conditions and the potentials, then the solution comes out as I plotted before. The physical understanding behind it is that the eigenvalue that is picked out by the hidden phase is the one that inflates the most. And through the flux that transitions at the endpoint, the visible phase somehow knows about the expansion rate of the hidden phase, and through a long enough time wants to come into equilibrium with the hidden phase. In equilibrium, everything has to be expanding at the same rate. So despite being in the classical regime, the flux is always going down, but in a sense, it's being continuously injected at the edge of the boundary. So the flux is continuously injected and continuously going down, but despite individual trajectories always going down, the ensemble average is still peaked at this point because the eigenvalue that is picked out is the one that has to inflate at the same rate as the hidden phase. So it's a bit like in thermodynamics. If you look at trajectories of individual particles, then looking at a single particle, there's no preferred value of the velocity of that particle. it's only when you look at the ensemble of the trajectories of the particles do you get a peak in the Maxwell-Boltzmann distribution. And when you put this ensemble in contact with another box of particles, even if it's very weakly in contact, through a long enough time, the ensemble will come to some equilibrium and may change the average velocity of the particle.
Okay, very interesting.
So
But as an
this is,
observer living in one particular patch won't be able to know such a boundary condition.
exactly. To that single observer, anywhere along the potential of this visible phase is as good as any other. But it's the ensemble that is in equilibrium with this hidden phase that leads to the maximum eigenvalue being peaked here. Yeah.
Yeah. Thank you.
I see. It's interesting. Yeah. So for visible and hidden sector distributions, the visible sector distribution knows the change in the vacuum energy in the hidden sector somehow, right?
Exactly.
So that is the point that you are sensitive to the visible sector is sensitive to the hidden sector. So yeah, the large volume effect is still important for the visible sector, right?
Exactly. It's the flux conservation at the transition point that that allows, in a sense, the coupling of these two to know about each other.
Yeah, yeah. It's a mixture of quantum and classical phenomena. So it's not that easy to follow. I'm used to. I mean, most of people are used to solving the classical equation motion. So, and do you have? I mean, also, are there any? But if you don't have any other question, I didn't understand. About the Higgs mass, the application to the Higgs mass. You said the scanning scalar field. There's the phase transition at 5 plus, right? And then
yes,
for which the Higgs mass becomes negatively large. It could be negatively large. And then what about the Higgs quartic coupling? Does Higgs quartic coupling becomes negative at that point, or what is that?
So the quartic here is not being scanned by phi, but it does go negative just through RG running at large Higgs values. So this is why there is always this UV phase.
And how do you know? How do you know there is another vacuum? I mean, the lambda changes. Yes, but so you are also scanning Higgs mass, but the Higgs quartic coupling runs independently.
Yes, so we assume that at the EFT cutoff, something restores the potential. So yeah, so in the standard model, this would just run off to negative values once the Higgs quartic RG running becomes negative. So the reason why there's the existence of this UV vacuum is that at the cutoff of the EFT, say at 100 TeV or 10 to the 6 GeV or something, we assume that some new physics there will restore the running of the quartic, so that there is a UV vacuum.
Yeah. So yeah, okay, yeah. So for that scenario, you need you are making the instability problem worse by introducing
like exactly
fermion.
Yeah. We need to make it. So yeah, that's the tension between lowering the instability scale, but without making the potential more unstable. So we have to add vector-like fermions to make this turnover happen earlier. But we also checked by solving the bound solution for the tunneling probability is still sufficiently long-lived for a vacuum to not have decayed away. So we're still safe. despite a low instability scale.
Yeah.
And this actually crucially requires a higher dimensional operator contribution
Mm-hmm.
to. So in the example we give, we add a dimension 6 operator, h to the 6th, so as to make the potential sufficiently stable that we haven't decayed away, despite the vector-like fermions lowering the instability scale.
So I want to study more. So are there questions? I mean, Shintaro, you can take the question from.
Is there any other question or comment?
It's a nice summary of 100-page long paper.
Thanks.
I'm still in the middle of 20 pages.
Most of it is technical results in an appendix that that are not really necessary for the bulk of the story. I mean, I think for this example in particular, it's really just solving the FPV for a linear potential on the visible phase. And once you do that in general, and you set the non-vanishing boundary condition on the edge, then the solution depends on some eigenvalue, and then you just plug in this eigenvalue that you get from the hidden phase solution, and that's really all there is to it in some ways.
Can you comment on the? You might also had a small discussion on the connection to swampland conjectures. It's you are motivated somehow, partially. Are you in the swampland?
Yeah, I mean, the only real bearing the swampland has on this is that the swampland seems to suggest that very flat potentials are ruled out by swampland distance conjectures. And as I probably didn't emphasize enough that the reason that we are in eternal inflation is also because our potential has to be very flat. So we don't want phi to roll away from the location that it was peaked at during inflation. And if you put in the constraints on on dark energy for the W parameter not to be beyond the observed values, then phi must be on a very, very flat potential to not slow roll too far. And such a flat potential seems to be disfavored by swampland conjectures.
And also the non-internal inflation, you are focusing on you are free for non-internal inflation. Because of that, the swampland conjecture somehow.
Well, our mechanism requires us to be in eternal inflation. And the swampland distance conjecture seems to suggest that eternal inflation is not possible. So
yeah, right.
There is some tension there.
So if there's no further question, let's thank Tevong you. Thank you very much.
Okay.
Great. Thanks for having me.
Thank you for your nice talk and for nice discussion.
Thanks. Hopefully see you at CERN.
Okay.
At some point.
Yeah, sure. Okay. Take care.
Bye.